Bob Murphy Show, episode 314.
There's a tidal wave coming. What you gonna do?
Get ready for another episode of The Bob Murphy Show, the podcast promoting free markets, free minds, and grateful souls. It's your source for commentary and interviews, conducted by a Christian and economist. Now here's your host, Bob Murphy.
Hey everybody, welcome back to the Bob Murphy Show. Today we've got another learning episode. We're going to get into some math and some computer science. My guest is Winston Ewert, who is here to discuss his new chapter in a book titled the name of the chapter is titled The Human Mind's Sophisticated Algorithm and Its Implications. So just to give you some context here, Winston, we had on the show back in episode 111, that was in 2020, I believe. And at that time, I was explaining that he was this up-and-coming researcher in the ID movement, intelligent design, and he had actually co-authored one or more articles with William Dembski, who's like one of the, let's say, top three. At least he was back then. I don't know. I haven't kept up with the literature in that movement. And so the fact that Winston was co-authoring with Dembski, told me that, oh yeah, this guy's the real deal. Like the leaders in this movement, must be giving him their blessing. So we had him on back then to talk about he had been applying results from computer science to biology. So similar sort of thing that he's doing in the book chapter today that we're talking about, but it's more about, the opening line of this chapter is the human mind a computer? If not, what is it? Before we can answer, we must first clarify what exactly is a computer, right? So he goes through and then he just starts, giving some standard results from computer science and then applying that to the human mind, which is not the same thing as the human brain, incidentally. Okay, so that's what goes on here, and it gets into some cool math with, as you can imagine, Gödel's theorem, the Goldbach conjecture, the halting problem, a famous problem, from computer science. So all kinds of good stuff there that has deep implications. Whether you like the intelligent design movement or not, I think you're going to find this an interesting discussion. But that is the broader context of what's going on. Also, just to connect the dots, in this book chapter, at the end, in the end notes, some of his references, he includes a reference to a paper by Jonathan Bartlett, and that is the same guy that we recently had on back in episode 303 of the Bob Murphy Show, where we had Bartlett on to talk about how random mutations aren't always so random, if you remember that one. All right, so a lot of these guys are coming out of the woodwork. It's almost like it was planned, Doesn't seem random that these guests are all related. There seems to be a pattern here. Without further ado, here is my discussion with Winston Ewert. Winston, welcome back to the Bob Murphy Show.
Hey, it's good to be back.
So you have sent me this intriguing, it's what, a book chapter?
Book chapter, yes. The
chapter
book
22.
question, Mind in Your Brain, and I've got one chapter in it.
Yep. The Human Mind's Sophisticated Algorithm and Its Implications. And so, folks, Winston and I were chatting before we hit the go button here, and I think the only way to really do this is just to kind of go through the whole chapter and just, summarize the main points in each little section, because otherwise I think people, they're not going to get the train of argument. So I guess maybe big picture, do you want to give the overall context here and like what are you trying to accomplish with this chapter?
Okay, big picture. Yeah, so the big picture is looking at the human brain and asking, is it an algorithm? And if it is an algorithm, what does that tell us? And what kind of conclusions can we draw? a lot of people, they want to focus on the issue of consciousness, or sort of why we have awareness of anything. I talk a little bit about that, but then I talk mostly on what problems humans can solve. And in my assessment, there's not really a good case that humans can solve problems that computers couldn't if they had sufficiently sophisticated algorithms to operate on. But then what I argue is, based on some theoretical computer science stuff that we'll get into, that I think humans aren't capable of creating an algorithm as sophisticated as themselves. And we can create, ever more increasingly sophisticated artificial intelligence, but we're actually going to be limited to what we actually have ourselves. And that has implications in terms of the future of AI technology and what it can do, and also our own origins, because the implication is that we must have originated from something which isn't limited by the kind of intelligence we find in artificial systems.
Okay, very good. Now, just a quibble right there, when I asked you to summarize, you actually said the human brain. Would it be better to say the human mind?
So the question is, like, do you think that the human brain is beyond the mind and all that? So I can't, of course, remember the exact words I just said, but certainly I'm talking about what the human mind is able to accomplish. And I suspect that most of what the human mind does on a computational or thinking level is, in fact, reducible to the brain. And if there's a part of the brain which is beyond the brain, I would attribute consciousness or something like that to it.
Okay. I'm just saying, because your chapter is like the human mind's algorithm, and then your first sentence is the human mind a computer.
Okay.
And then, like I said a couple of minutes ago, when you just summarized, you were talking about. So the question is the human brain? And so I didn't know if in your mind, no pun intended,
so mind
those were interchangeable.
may have flipped a little bit. Obviously, I think you can distinguish between these two things, and to what extent the mind is generated by the brain is a question of debate.
Okay, great. Okay, so on that note, then, just diving in here, you start out and saying, is the human mind a computer? And so then you say, well, to answer that, we first need to know, what do we mean by a computer? So do you want to explain what you think the right way to define a computer is?
Yeah. So a computer, as we think of it in computer science, is a machine capable of following a defined procedure. So historically, before we had electronic computers, we had human computers. And these would be people whose job it was to sort of go through calculations by hand. And they used to have banks of these people called computers, and they would use them for sophisticated things, like early days of NASA use them in that sort of thing. So the thing that made them computers is there was no creativity or anything in their job. You just have to follow this precise procedure. And that's essentially what distinguishes a computer from anything else, is a computer is following some sort of precise procedure.
Okay. And let's see. And so then the question then is, so like the sorts of things, what do we want to say? Like, can every task that we want to be done be reduced to a procedure or an algorithm? Is that the next issue to tackle?
Yeah, I guess. I'll have to. If I thought through what we were going to do exactly, I could have had a thought what the different steps would be. But essentially, yes, I guess the next thing.
We're trying to reduce this conversation to a step-by-step procedure.
Yes, we are, and unfortunately, that's harder to do on the fly.
And right now, the viewer's wondering if there's going to be a halting issue with this.
There may be a halting issue. Yes. Okay. So then the question is, when we're asking whether a task can be done by a computer, what we're asking is, can you reduce this to a step-by-step procedure? And that's essentially what a software engineer's job is to take tasks which other people have and reduce them to step-by-step procedures so the computer can do them. It's really obvious that you can reduce some things to a step-by-step procedure, like calculating long division. You were probably taught how how to do the step-by-step procedure to do long division, all kinds of other mathematical things in school. And you may even remember what those steps were at this point in time. And you can imagine procedures for more complex things, like figuring out the longest word that you can put on a Scrabble board given the tiles you have. You might be able to think through what would be a step-by-step procedure to check all those words. And so you can imagine that. But if you were to ask, write a step-by-step procedure to write poetry, that would probably stump most of us. Although nowadays you can ask ChatGPT to do that. So someone seems to have figured out how to produce a step-by-step procedure that manages to produce poetry. Maybe it's not as good as human poetry, but still you can do it. And so there's certainly a lot of tasks that can be sort of reduced to these step-by-step procedures. And there are other tasks that we don't know how to reduce to sort of a simple step-by-step procedure.
Okay, and it's not just that on some of them we don't know how to do it, right? Like, do you want to speak a bit to the, they've literally proven the limits of this type of approach?
Sure. We know, Matt, and it's sort of foundational proofs in computer science, that certain tasks cannot be reduced to a step-by-step procedure. And there were some famous problems in mathematics that were basically come up with a step-by-step procedure to do this, and we actually proved you couldn't. The most famous example is called the halting problem. And the idea of the halting problem is that I'm going to give you a program. And remember, a program is just a step-by-step procedure. And I ask, if you go step-by-step through this procedure, are you ever going to reach the end? Or are you going to end up, getting caught in a loop somewhere in there? So that you get to step 10, it tells you to go back to step 1, and you just repeat those steps over and over again? Or do you eventually reach the end? And so that's the halting problem. And we know mathematically, it's proven that it's impossible to write a program that can, for every possible input, for every possible program you could feed it, to determine whether or not it halts. And that actually turns out to be sort of equivalent to the Gödel's theorems of mathematical impossibility, which I know you've talked about previously on your podcast.
Okay, so let me just restate that, Winston. So for people who aren't totally familiar with it, like a old school computer program is like, they used to have the lines would be numbered.
Line numbers, yeah.
So like 10, space, print quotes, hello world, end quotes, 20, go to 10. And so that program is just going to keep printing hello world forever, until it runs out of electricity or the computer breaks or something. But intrinsic to the program, that's just going to repeat forever.
Yes.
Whereas a different program that says line 10, print quote, hello world, end quote, 20, end, that program ends.
Yes,
that's clear. We can just look at that and know, yep, that program, there's a halting in that program. And then, of course,
programs are pretty obvious.
Right. And it's just to show people what do we mean when we say these things. But then in general, something could be a lot more complicated, and you could run into a certain thing, or maybe you could say, oh, if the user types in this, then it's just going to loop forever, and and
usually exclude user input from the equation.
Okay, fair enough.
There's a mathematical truth. It either does or doesn't eventually halt.
Okay, that was actually something I was going to ask you about in a second. Okay. So that's it. And so then what the claim is that has been proven, so it's a good claim, a solid one, is that you cannot. We have no procedure. We have no way of writing an analysis such that if what you feed into it is any arbitrary computer program, that this thing can tell you yes or no, this program will halt or it won't.
Right.
It is impossible for us to design a procedure that would give us that answer. Is that technically the statement?
Yes.
Okay. And then what's interesting, like you say in the paper, is you might think, well, why don't we just test it for any given program? And it's like, well, you could run it, and 16 million years later, you check it, it's still running. Technically, we don't know that it never halts, because maybe it's going to halt after 17 million years.
A little bit more, and it would have halted. Who knows?
Yeah. So clearly, if it stops, then that means
then
it halts. But you can't prove the other way. So what actually I was going to ask you, Winston, is what if the program says line 10, pick a random number between 0 and 1, and then line 20 says if it's less than 0.5, go to line 10 and otherwise end.
Yeah, when we're doing this in theoretical computer science, we say you can't have randomness or user input. So it has to be deterministic. Once you run the program, it's true or false, it halts or doesn't.
Okay.
There's no inputs or anything coming into it. Any input has to sort of be put into the program at the beginning.
Okay. Everything's got to be like endogenous to the system or something. Okay. Yeah. Okay, fair enough. So that's a result. And again, folks at home, it's not just that they're saying, oh, we've encountered some programs and we're looking at it and we're not sure whether that's not the claim. The claim is they can prove mathematically that there does not exist in general a way of evaluating such programs. And then, like you say, Winston, that is analogous to the, what Gödel showed famously, and folks, I'll link to it, that it was an early episode of this podcast, that in general, if you try to construct an axiomatic framework for mathematical propositions, thinking, let's just really build on a solid foundation and have everything just be rigorous, that for sufficiently powerful statements, like to be able to say there exists or for all X such that, if you have the ability to make statements like that, then fix your axioms, you have your rules of transformation and whatever. You can always, within the world of that system, write a proposition that says this proposition cannot be deduced from the axioms. And so then the problem is, okay, that's either got to be true or false. And so if it's true, then, there's a true statement we can write in the language of this system, and yet it can never be proven from within the system. So that's weird. It's true, but it's unprovable. Or if it's false, then that means this statement can be proven in this system, and then, oops, it's inconsistent because now we're saying you can use the axioms to prove something false. So then the normal conclusion mathematicians take from that is, since we hope that math, the various branches they don't contain contradictions, that means there are true statements we can write in math that even in principle we can never prove. And that's kind of mind-blowing when you just sit there and ponder that. So, okay. So that means then, Winston, back to, your argument that there are certain tasks that even in principle, a computer, if we're defining it as a machine that follows procedures, can never accomplish, solve. Yeah. Okay. So what, I guess, how do you want to take this now? Do you want to say, so does that mean the human mind is able to solve those ones too, or?
Right. So that comes into the human mind. So a lot of people are very interested in the halting problem because they would like to say, the human mind can do things that computers can't. The problem is that you would have to not only show that computers can't solve this problem, you have to show actually humans can. And the truth is, if we were to look at examples of programs that a program couldn't prove halt or not, a lot of the time humans couldn't answer that question either. Because you can construct a program that is based on the Goldbach conjecture, which is a conjecture in math. Basically, the point is that either there's a counterexample to this rule or there's not. And so you could write a program that sort of goes through all the numbers and checks for a counterexample. And then so if it finds a counterexample, it stops. And so you have a program there that either goes forever or finishes, depending whether this conjecture is true or not. Now, we've never found a counterexample to this conjecture. We've also never proven it. So humans can't resolve the halting problem on that program either. We guess it's probably true because we can't find a counterexample, and we've tried really hard to find one. But humans seem to be kind of in the same situation as these programs, that they can't solve all of the halting problems.
Can I stop you, Winston? Let me just make sure, because this part was blowing my mind in your paper or your chapter.
This is my goal: blow your mind as much as possible.
Yes. So let me just make sure we're not missing people, or people aren't missing out here. So the Goldbach conjecture is states the conjecture is that every even number greater than 2 can be expressed as the sum of 2 primes. All right, so prima facie, I'm shocked that is even possibly true. Like I wouldn't have, that seems like how
It
could
is,
that possibly?
it is kind of counterintuitive that seems that
I'm glad you agree with it because first I was like, no. Whereas something like Fermat's last, like seemed like, oh yeah, that seems plausible. But this one, I can't even believe it. And so what? And just to make sure people understand so 88 is an even number greater than 2, and you can express that as 17 plus 71 equals 88, and 17 and 71 are both prime numbers, right? Okay,
Yes.
so that's the deal. And then so the Goldbach conjecture is that for every, you just keep adding 2, and each new number you get that's an even number greater than 2, there exists 2 primes, right? I'm stating it correctly what the claim is,
Yes,
the conjecture.
that's correct.
And then you say, this rule has been checked for all numbers up to 4 quintillion. Okay? And so there were, a bunch of grad students that for years have been toiling away at this. And so,
Poor grad students.
yeah. So the point the point is we can't prove it. It
Right.
hasn't been proven, but they have checked it. They haven't found a counterexample yet, because all it would take is to find one even number that, if we could somehow show, no, there's no 2 prime numbers. But so far, up through 4 quintillion, there's no counterexamples that they found to this. But technically, they haven't, you can't check all infinite number of even numbers.
Right.
And so that what Winston showed here in the chapter was to say, if it weren't for the halting problem existing, then we could solve this problem. And at first, that might seem like, what is talking about whether a computer program ends have to do with this thing? And his point was, consider this program. So I think I just should read it out, Winston, so people really get what we're saying or what you're saying. So line 1 says, start with the number 4. I mean, we're speaking in plain English here, but you could, translate it into C++ or whatever. Then 2 is determine whether that number can be expressed as the sum of 2 primes. If it can't, then halt the program, end. If it can be expressed as the sum of 2 primes, then add 2 to that number and go back to step 2. Right? So it's a pretty simple program. You'd have to have a subroutine to know, to determine whether a given number can be expressed as the sum of 2 primes. But suppose you could delegate that and do that. So have a subroutine that did that. Okay, so now Winston's point is, if we ask, does this program halt or not, to be able to answer that, you would implicitly be solving the Goldbach conjecture one way or the other.
Yeah.
And so that's this, and then he kind of just elaborates and shows in general, for any type of task that you can reduce to a set of, procedure, you could go ahead and solve that. If, you could write it into a computer program either way, and then to be able to say whether this program halts or not would be equivalent to saying that, oh yeah, this claim is true or not. Okay, so now where do we go?
So what I argue in the book is that the halting problem is the Uber task. If you could solve the halting problem, if you could have some procedure that would quickly and easily tell you whether a program halted, you could solve any problem of intellectual task that you might have. So one example is the sort of mathematical test. Is this true or false? If you could solve the halting problem, you could do them. I also look at mathematical proofs, because we could write we might want to know, is there a proof for some proposition like the Goldbach conjecture or anything else? Because we don't actually know whether you can't prove the Goldbach conjecture. We just haven't found a proof. But you could conceive of a program that, just like it counts through all the numbers to try and find a counterexample, it could systematically go through all possible proofs, starting from the shortest proof, working its way up to longer and longer proofs. And if a proof exists, it's eventually going to find it and then halt and say, here's the proof. If the proof doesn't exist, it'll go on forever. So if we could solve the halting problem for this sort of proof checking program, then we could know once and for all, does a proof exist for the Goldbach conjecture? And so in some ways, finding a proof seems kind of very different from trying to find a counterexample. Mm-hmm. But if you could solve the halting problem, you could do both of those things.
Right, and just to make sure people are getting the argument. So to say, does a proof exist, like we must specify the syntax, like what's the notation we're going to use or whatever, right. Like the axioms and blah blah blah. And then you could just define, you could see, okay, let's say proofs that are up to 100 characters long. That's a finite space, and you could just systematically search through all possible, attempted proofs that, and then the computer could just independently, in other words, it's fairly easy to check whether a given purported proof is valid or not. That's not hard to do.
Right.
And so the computer could just generate, everything that's up to 100 characters, every possible permutation, every character you could put in each little placeholder, and then just systematically check all those and say, through that set of all possible proofs of that length, did any of them correctly, validly prove this conjecture? And if the answer is no, then you could say, okay, let's now look at 101. Or you could just expand the length of, the space of possible, the length of the proof, and you could just keep doing that. And so then Winston's point is, if a proof does exist, that means in principle that procedure, after some finite period of time, should hit the proof, right? Because the proof's not going to be infinitely long. It's going to be finitely long. And so this program will hit it at some point, in principle at least, even if it's 60 quadrillion years. And so then if you had an airtight way of always saying whether a given computer program would halt or not, then, that it's a backdoor into that answer. Was what I just said okay?
That was great.
Okay. So what's interesting, Winston, and I don't know if you care about this or not, but isn't it, something seems funny, like, suppose somehow you did, the point is you can't, like the halting problem is a thing. It's a problem. But imagine the computer, like you did have this independent thing that's for some reason you could trust, and it said, oh yes, this program will halt, meaning at some point it would stop because it will find the proof. Mm-hmm. Would mathematicians say, okay, so that means the Goldbach conjecture or whatever it is now proven, even if they didn't actually see the proof? If they just knew, oh, we know a proof exists, you know what I mean? Like, isn't that seems like it's one step removed from.
So it would depend on their confidence in the oracle.
Yeah, fair enough.
And if you get down to it, you could adjust the program. So like, only consider proofs that have this property. And, oh, that one, didn't halt. So I now know the proof has this property. And you could actually narrow down the proofs by repeated applications of the procedure.
Okay, so you're saying
once so if you have the halting problem, yes, the halting problem gives you a yes or a no, but you could, figure out details of it by sort of adjusting slightly the question you were asking by the program you inserted.
Okay, it's sort of like asking 20 questions.
Yeah, you're asking 20 questions. So
yeah,
if you had this, you could actually reconstruct the proof.
I get what you're saying. So really, what you've done is, after a while, well, yeah, you would know the proof exists, and then you could start, winnowing it down a little bit. At least you get more and more of a flavor. But anyway, that still isn't intriguing to. I guess it would depend on if you knew what the math was behind proving, our solution to the halting problem. Then that would, you know what I mean? Like you're right that it's the reason to me it seems like that wouldn't really be a proof, is because I'm thinking it's a separate thing, and like the math's over here, but then over here we're just qualitatively saying, no, we know whether the program will stop or not. But if that itself were a proof that it actually worked, then you really would be proving the original proposition. All right, so that was kind of a digression, but
yes, I'm sure everyone listens to the podcast for your great digressions. So.
Okay, so now I'm not sure how do we.
So I also argue that the same thing applies to things like detecting patterns.
Okay,
it's a little more involved, but essentially the idea is that any pattern has by virtue of having a pattern, there's a short program that describes it. And just as we look for proofs or counterexamples, we could look for short programs that describe things. And so you could very much the same way get a sort of detecting when something is a pattern. You could also get predictions by simply looking at what's the simplest thing that would extend this pattern, which is essentially what we're doing when predicting things. And very much along the same lines, if we could have a halting problem, we could find the simplest description that would fit some additional data and then figure out what data is most likely, and we could use that to make predictions. So all of these different ways, I argue, show that basically I think actually, any intellectual tasks that humans take on, you could construe as trying to find the answer to certain halting problems, that you have a certain program that would sort of be yes or no, and the humans are trying to figure out the answer to it. So if you had the oracle that could solve any halting problem, you could answer any question, whether it's pattern detection or predicting or any of these things, that you would actually be able to answer all of these questions if you could just solve this uber task, the halting problem.
Okay, can I ask you for a moment or to take perhaps a digression? This issue of pattern recognition. So you've gotten in your chapter the example of strings of zeros and ones. And so the first one I think was real simple. It was just alternated, right? It was 0, 1, 0, 1, 0, 1 like that. And so if you ask somebody, hey, is there a pattern in this data? They would say, yeah, it just keeps alternating between 0 and 1.
Yes.
Okay. And then you could see your next one, you could say it's 1, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0. And you've got a pattern there that, the third one, you have a pattern there. And the second one, you're saying, oh, that was just randomly generated by my computer.
Yeah.
So clearly you can imagine folks having more or less complicated patterns that would take some study that wouldn't be as obvious zero. So my question, Winston, is for any finite string, I mean, the reason I know that the second one there is random is because you just told us, how I got this was asking my computer to randomly generate them. But strictly speaking, I'm sure there exist, functions that would produce that as the first, n elements. And so do you understand what would it mean to look at something and say, oh no, that's random? Like, doesn't that just mean we don't know what could have generated that? But in principle, couldn't you always could you ever prove something was random? That's what I'm trying to say.
Yeah. So in theoretical computer science, we have a notion called Kolmogorov complexity. Mm-hmm. And the idea is that we ask for a given finite binary string, what's the shortest program that generates this string? And so we sort of define randomness as there's no program. Things just started spinning. Oh, I'm back. Okay.
Thought I might have lost the connection. Can you just start?
Start again.
It was the definition of Kolmogorov complexity.
Right. Okay. So Kolmogorov complexity is the length of the shortest program that generates a particular binary string. So a very short program produces that 10 10 10. You could imagine the program does is very short, and more sophisticated patterns might be longer. But the theory is that there is no short program that generates a random string, because you would have to put that random string into the program.
Okay.
And so we would say it's random because there is no short program. Now, it's true that if there's just random string, it can be hard to tell that it is random, because maybe there's just a pattern that you haven't detected yet. Once I show you the pattern, usually, it's very clear the pattern's there. But it's true for just a generic random string, it's hard to prove there isn't a pattern. And that's effectively you trying to solve the halting problem, because you're saying, if I search through the list of all these programs, would I find one that produces this random looking string? And you'd like to know yes or no. And the halting problem could check all those strings if you could solve the halting problem. But since we can't solve the halting problem, that doesn't work. In practice, we look for patterns, and we're sort of can solve parts of the halting problem, but not in the general case.
Okay, so let me repeat that. So if we look at a given string, if we can discover a relatively parsimonious program that can generate that thing, that doesn't just need to take as one of its inputs or arguments the whole string that we're trying to explain, then clearly we'd say, okay, that's not random, right? Because we can generate that from a much simpler rule, that, you know, if a machine were to, or a computer were to follow that rule, it would generate that. Okay. If we're looking at something and we can't discover such a thing, we would say it has the appearance of being random, but technically we don't know. We have to remain agnostic. We can't conclude that it is random because there might exist some simple rule that generates this that we just haven't been able to discover.
Yes.
Okay.
Sort of that's like the whole idea behind stenography, where you're trying to hide information that looks like randomness. It's all sort of trading on that idea that you can't prove that something's not random. No, you can prove that something's not random, but you can't prove that it is random, generally speaking.
Right. Okay. All right. And I think people see why this is going to, at some point, intersect with the intelligent design debate, but let's keep going methodically.
Let's see. So then that gets there. So the point is you can't solve the halting problem. However, you can solve limited versions of the halting problem. So we can imagine a program that doesn't say yes or no, it halts. It says yes, it halts, no, it doesn't halt, or I don't know. And so obviously, you know, you can imagine a program that, you know, finds some very easy cases and says, yes, these halt, and some very easy, yes, this obviously loops cases, and says, I don't know, for other programs. And so you could very easily construct a limited halting detector. And the point being that, well, you can't solve all the halting problems. You can't do this for all programs. You can devise a program that will, for some subset of programs, solve the halting problem. And I talk of those I call those partial halting detectors, because they partially solve the halting problem.
Okay. And we ourselves were those, because earlier on we said that if it says print hello world, go to 10, hey, that's one that never stops. And when it says print hello world and end, that does stop. So my mind is a partial halting detector. Yeah,
so that's definitely true. We're all capable of figuring out for some programs. Some of us can figure it out for more programs than others. And I point out that if you had a halting detector, you could actually use it to verify the correctness of a partial halting detector by running through all the programs, trying to find one that gets wrong. And so that's sort of lays out understanding the theory behind halting detection, is sort of the first, that part there. So then the question we turn to is, how does this actually compare to human mind? And as we just mentioned, humans can solve some halting detection. Words. Humans are capable of solving the halting problem sometimes, and humans indeed are capable of solving the halting problems in many more cases than computers can, at least in our current state of algorithmic development. But we can't solve all of the halting problems. And you can see this also plays out in all the different kinds of tasks they argued were sort of subsumed in the halting problem. So humans can find counterexamples to some mathematical statements, but not others. We can find proofs for some things, but others we don't know if there's a proof. We can see that there's patterns in some things, but others we're not sure whether or not there's a pattern. We can figure out what the most probable prediction is in some situations, but not all of them. So in many ways, we kind of look a lot like we're a partial halting detector. We can do it part of the time and not others.
But can you explain, why did you say humans are better at it than computers are? Did I understand that?
So humans are, so if you looked at like the most sophisticated, well, if you look in any individual case that's a part of the halting problem, like finding mathematical proofs or finding patterns, humans have exceed where computers are on all of those cases. So human mathematicians are better at finding proofs than the best computer solving systems. And they're better at finding counterexamples to conjectures than the best systems. and they're better at detecting patterns than the best systems we have. And there are, some tools that explicitly try to solve the halting problem in partial, and of course, only some of the cases, but they will not solve all of the cases that sort of a person could if they would sort of investigate it.
Can I ask you just to make so the listener and me too understands exactly what you're claiming? So when you say, like, I get how if there's an open question, I understand what it means to say humans in general. I might trust the human mathematicians to find a proof for that rather than GPT-4 or something.
Don't go for GPT-4 for your math proofs. It's not going to go well.
But when you say counterexamples, that one, I just want you to explain more what you mean. Like I could imagine a certain limited class of conjectures where I would think the computer just with brute force would be able to find a counterexample faster than a human mathematician. Am I misunderstanding?
Yeah, I guess I'm kind of implicitly thinking if you're while using comparable resources in some sense. So yeah, a computer can actually exceed human abilities in areas where they can sort of brute force a lot of things because they can check way more cases than a person can very, very quickly. And there are certainly some cases like there's the four-color conjecture, which was proven by computers checking ridiculous number of cases and not a sort of short proof that mathematicians would prefer to have. So yes, there are cases where the computer ability to systematically check these things manages to sort of beat the humans because of that brute force aspect of it. The neat thing, I think, about humans really is that they don't seem to need to brute force in order to accomplish things that do require computers to brute force.
Okay.
All right. So I think the other important thing that I perhaps showed up a little early in my chapter that we missed was the point that, yes, you can construct a partial halting detector, but for any partial halting detector, you can think of and build an even better partial halting detector. So for any partial halting detector, we know there are programs it doesn't detect correctly. And so we know we could at least augment that halting detector so it detects one of those additional programs. And so there's always a better partial halting detector. So there's sort of this infinite line of increasingly better halting detectors that we know must exist.
Mm-hmm.
And so what the argument I put here is I think humans appear to be very far down the line. They're very sophisticated down this line of partial halting detectors, but they're not, infinitely the end of it. They can't solve everything. And so they're more sophisticated than our current computer technology and probably more sophisticated, I think, than our technology is capable of reaching. But they're still sort of somewhere on this line of increasingly sophisticated partial halting detectors. Let's see. We talked about Penrose's thing. Let's see. How can I?
Yeah, I was gonna say like that's another big one. I don't know if you want to do any clear the underbrush first or just jump right into that.
Right. Okay, so is it Roger Penrose? Am I getting his first name correct?
Yeah.
Okay. So Roger Penrose is known, I think his book is The Emperor's New Mind. And so he's argued that the human immutability is not computational. So that's sort of in contradiction to my suggestion here that human mental ability is computational. It's just very, very sophisticated. And he does it by appealing to Gödel's theorems. The basic thing so some people have tried a very simple argument saying, well, humans have proven this incompleteness, and that proves that they can do something computers can't. But computers have also managed to prove the incompleteness theorems using some computer proving systems. So that's not there.
Let me stop you, because
Yep.
that's an intriguing, like all these things. Like if you just sit there and hang out with the kids in the frat house, and just ponder it. So, and also just to make sure I understood what the argument was.
Yeah.
So some people might, and I've seen plenty of people do this. They'll take Gödel's results and they'll say, oh, so in a sense, we humans are above the mere machines or whatever. Because look at where Gödel, going through the Gödel's demonstration, his proof there, we know for any given axiomatic framework, there exist true mathematical statements in that framework that can never be proven to be true with those axioms, and and the rules of this is the valid way to go from a prior statement to a next one that is a logical deduction in that system. So we're like external, and we know, like that's that statement that says this statement cannot be derived from the axioms. That's a proposition in that logic, in that framework, axiomatic framework, and we know it's true, but it can never be proven to be true in that system. So no computer could prove that, because by definition, or not by definition, but by construction, that statement cannot be derived from the axiom. So the computer can't prove it, but we humans know it's true. And how do we know it's true? Well, we didn't prove it with step by step from the axioms. And so it's like we humans have the ability to grasp truths that are above mere axiomatic frameworks. Or so people say stuff like that. And then you're saying,
so I'm saying, well, yeah, I mean, if you look at the proof of Gödel's theorem, like, well,
that's a proof. Yeah, so a computer can do that.
Well, a computer could generate that proof, and computers have in fact generated versions of that proof.
And so the same way that we know the Gödel statement in a given framework is unprovable, a computer can do the same thing and reach the same conclusion. So there's nothing special about us doing that.
So that doesn't work. But Robert Penrose has a more sophisticated version, and I need to remember how exactly his version goes.
Okay.
I haven't thought about it since I wrote the chapter, apparently. Okay, so what do you say? Human cognition is very conditional. There's a formally definable system of logic they're following. We can thus construct a statement of form. The statement cannot be proven. This is called the Gödel statement. If a statement in human is logic consistent, then it cannot prove the statement is true. The only alternative statement is true. But this creates a contradiction because the humans were able to determine the statement was true, which did not follow. Okay. So the argument is, from Penrose, basically that if humans could formalize their entire system of logic that they operate on, and then they could say, this system of logic can't be proved, this system of logic can't prove this statement. Then they would have a statement that they know is true, but they couldn't prove it using humans' internal system of logic. And that might be a little mind-bending. The basic point being, there's some statement that sort of says, this statement cannot be proven by humans' internal system of logic that we operate on implicitly. But then we would have a statement that we know is true, but which claims that humans couldn't prove it was true by their own internal system of logic. And so based on that, Robert Penrose says, well, the only way out of this conundrum is humans aren't computational. They don't really operate on a system of logic in that sense.
Mm-hmm. They have ways of arriving at the truth besides just step-by-step procedures.
Yes, that's the idea. Now, for that to work, it actually requires that humans could actually sort of write out the complete system of logic that they're operating on. And because you need to do that in order to say this, to know exactly what the statement is that you can't prove. Mm-hmm. Because embedded in that statement is, this is the human system of logic. And so my argument would be, well, yes, humans aren't capable of writing out their complete system of logic. They can't create an artificial intelligence as powerful as themselves. But perfectly consistent with they wouldn't be able to write out a Gödel statement. And Penrose is actually aware of this issue. And he says, well, how would humans happen to have this really sophisticated system? And he says, well, the only way they could do that is if divine intervention gave it to them. So I think as he puts it, the argument only follows if the argument underlying human mathematical reasoning is knowable. And instead, if mathematicians follow an unconscious, unfathomable algorithm, which is what I think is going on, his argument doesn't work. But he says he thinks it's so difficult to explain the origin of humans operating on a really sophisticated, unfathomable algorithm that the only way that could arise is through some sort of divine intervention, and therefore that can't be what's going on.
Okay, let me make sure I'm following you and take the listeners along with it.
Yeah.
Okay, so one thing to make clear is you can't just say this statement can't be proved. What Gödel did is he showed, for a given axiomatic framework, like how you would actually construct the Gödel sentence, right? Like just like in English, I can say right now, I am lying to you right now, or this statement is false, and it's not like the universe blows up. Like, oh my gosh, you just, internal contradiction because it's English, who cares? Whereas if you're going to say, no, math, we're serious, it's very rigorous, and like 2 + 2 = 4, that's either true or false. So like what Gödel showed how, for, in a given framework, you can define the axioms, and here's the syntax and blah, blah, blah. And then he showed you this is how you construct a Gödel statement. And so Penrose is saying, oh, well, because, humans, we could construct, if we formalized everything that we do with our logic and blah, 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 then in that system, we go ahead and write the Gödel sentence, and then boom, doesn't that show? And Winston, your point is you can't just jump over, you can't just yada, yada over the formalizing the system. But that's kind of the point, that we rely on some loosey-goosey, shooting from the hip reasoning that maybe, that seems fine, but yet it's not like everything we got going on that we can just systematize and distill down into an axiomatic framework. Then once we had nailed that down, then we could go ahead and construct the Gödel. So do I have what your initial objection is? Correct?
Yes,
okay.
That in order to construct a Gödel statement, we would have to be able to systemize all of human rationale.
Right, and that's sort of, I don't know if it's raising the question or begging the question. I know people get really up in arms about the distinction there. It's one of the two, is to say, yeah, that's kind of the issue. Like one takeaway from Gödel's results is to say there's more to human knowledge than what can be axiomatically, distilled or whatever. And so by Penrose just saying, assume everything it is that we do, we could systematize into an axiomatic framework. Like that's kind of one of the issues under dispute. And then you're saying the way he's kind of aware of that issue.
Yes.
And then can you just explain again what he's trying to say?
So he's aware of the issue. He uses the word knowable, that in order to do this, human intellect would have to be knowable, that we could actually sort of articulate the reasoning that we're using. Mm-hmm. So if it's knowable, then we could construct the Gödel statement, and then we could know something is true that we can't prove according to that system. And he says, well, but if it's not knowable, and if instead it uses, I think he says, an unconscious, unfathomable algorithm. So if it's a really sophisticated algorithm that we're using we're unconscious of, that we couldn't actually articulate, it's not knowable, then his logic doesn't follow. And so that's something he concedes in his argument there. And his argument, but his counter to that is, well, where would that unconscious, unfathomable algorithm come from? He argues it's implausible that evolution could have developed a really sophisticated, unconscious intelligence algorithm for humans.
Mm-hmm. And so his conclusion is, therefore, it doesn't exist. So whatever it is that we're doing, it is knowable. We could codify it if we really wanted to.
Yeah. So his argument is that it's not a really sophisticated algorithm, because where would that come from? And it's not knowable, because then we could construct a Gödel statement. Therefore, we're not limited to an axiomatic system.
Okay. Got it. And then what are you saying?
So, it occurs to me we actually missed the linchpin of the argument of arguing that a Turing machine can only a partial halting detector could only construct lesser partial halting detectors.
Okay. So
And that's actually kind of an important part of my argument.
okay.
So the point being that in order to create a partial halting detector, you at least need to be able to verify that it works.
Mm-hmm.
And that is another Ewert task. And the particular way the proof works to prove you can't solve the halting problem essentially works out to pointing out you can't solve your own halting problem, right? The halting detector, you could write a halting detector that would solve some partial halting detection problems, but it could never solve the halting problem for itself. So a partial halting detector can't decide whether itself halts. It can decide whether some other partial halting detectors halt, but not itself. And so I argue what that implies is that if we're partial halting detectors creating other partial halting detectors, we can only create a partial halting detector less sophisticated than ourselves that can detect less programs' status than we can.
Okay.
And so I argue that in general, the only way to have for a partial halting detector to create another partial halting detector, it must create one that's less sophisticated, that's further down the infinite line of the sophistication of partial halting detectors.
Okay.
So
hang on a second. So from earlier pontifications, we concluded there exists in principle a spectrum of increasingly sophisticated partial halting detectors. Yeah. But what you're saying here is pick one of them, start using it. That thing cannot generate the next most sophisticated version.
Right.
Even though such a version does in principle exist.
Even such as disks,
it can't be
only generate less sophisticated.
Generated by that inferior version. Okay.
Yes. So
which sort of makes sense, because if that weren't true, then if you just had one, just let the things run and they would get increasingly better with each iteration.
All right. So then going back to Penrose.
Mm-hmm.
So Penrose says, well, the only way that humans could operate on this really sophisticated algorithm is if, divine intervention was involved. And of course, I do think that divine intervention was involved. And that the fact that humans seem to be highly sophisticated halting detectors is an indication that we were generated by something which has greater sophistication and intelligence than ourselves.
Okay. So are you telling me that we just proved the existence of God?
So I think if you accept all my arguments, the implication is, yes, that human intelligence must derive. And the thing is, you can't even say we derive from a more sophisticated partial halting detector, because then where would that come from? That basically we must have originated from something that is transcendent and beyond issues of partial halting detection and all of that to something beyond that. And I think the implication is the only answer to that is yes, something basically like God must exist and be responsible for our origination.
Okay. Let me make sure I'm getting the essence of your argument. So your argument is the human mind is algorithmic. Is that a true statement?
Yes.
And then
I should perhaps qualify. So I don't think consciousness is algorithmic. We didn't get into that side of the argument because that's not really a big contribution on my part. But human mental abilities in terms of like our ability to do calculus or prove things or think about things, that side is algorithmic.
Okay, what about this? Among other properties, the human mind is a computational machine?
Yes.
Is that a true statement in your framework? Okay.
Yes.
And then, so given that both you and Penrose agree, if that were true, since that could not have possibly come from evolution,
Yeah.
then that would imply there must have been something with a mind that was at least as good as ours or superior that gave us that computational ability, those computational abilities or framework or system.
Yeah.
And then, so then, in principle, okay, that stuff, it could just be, oh, maybe aliens came and seeded Earth a billion years ago, but then that would just, was it either raise or beg the question? Where did the aliens get it from? And unless their world was a lot different from ours, so if evolution doesn't explain how we got ours, them evolving, a lightning bolt hit the pond scum on their planet, and that's where that doesn't work there either. And so you just have this ever ascending chain of more intelligent beings bequeathing that. And so the only logical stopping point is a thing of infinite, the perfect halting machine.
Thing that can solve all the halting problems is the only stopping point.
Something with infinite intelligence. Okay. And so, that's obviously, a God, or at least has a lot of the properties of what we mean by God. Okay.
Right.
And Penrose agrees with you on that, but Penrose, the way he avoids that is just to say, right. So that's why I don't agree with you, Winston, that among other properties, the human mind is a computational machine. That I don't think that's a correct way to describe what it is that we do when we solve intellectual tasks.
The other exit say, the human mind isn't computational.
Right. Okay. So I guess, how does this fit into, if a standard computer scientist heard you saying that, what would they walk away and, start going to church, or would they say, where would they disagree with you?
That's a good question. I think they might try to wiggle out of the claim that a partial halting detector can only produce lesser halting detectors. So they would want to claim that somehow there's a way around that. So that is the point. So I think I even acknowledge in the chapter, I don't have a completely rigorous proof that it's somehow impossible to do this.
Okay, so just to be clear, that's kind of like a statement coming from Winston that's not like standard in information theory.
It's not standard in information theory that you can't of construct a partial halting detector. I sort of go into more detail in the book, arguing why this seems to be the case, that you couldn't do this. And basically it is standard that, the halting detection proof shows you can't solve your own halting problem. Now, my argument is that the implication from what we know in computer science would be that you couldn't construct or even verify that a more sophisticated or even equally sophisticated halting detector existed, or that it worked correctly.
Okay. Yeah. So to me, again, just hearing it in natural language, it sounds very plausible to say, if you have a partial halting detector of certain sophistication, it could not construct one of a higher sophistication and know that it had just achieved that outcome.
Right.
Because that's almost like saying, if it knew that, then it was already that good in the first place.
Exactly. So I think it's very compelling that that's the case. But I suspect if one wanted to sort of insist on the algorithmic nature of human intelligence, that's probably the point you would go after.
Right, because I can imagine they could say, they might have some kind of evolutionary framework and just say, well, no, you got the original system, and if it was in code, and it just randomly started changing its program through blind luck, it could happen to write a better one. But your point is the first program wouldn't know that second one was better.
It was better. And I think if you look at the evolutionary process, you can conceive the evolutionary process itself as a program that is sort of trying different things, trying to find the best thing. And so it itself is sort of falls into the same thing, that it would need to somehow have a process for verifying the correctness of your halting detection. And, it's got a limited ability to verify correctness by, does your bad decisions get you killed? But not nearly as sophisticated as we humans have. And I think you couldn't get that out of the evolutionary process.
Okay, and that kind of stuff pops up a lot in the intelligent design debate, where this, standard modern synthesis people try to like dish everything off to the environment and natural, a random mutation acted upon by natural selection, and then it's almost like, okay, so then all that information just is in the terrain, and so how did it get there? And so are you kind of saying it here that if they did have that sort of evolutionary mindset, then okay, that sort of raises the question then, why is the nature of the universe such that apparently it itself isn't a perfect halting detector?
Yeah. I mean, I would go two ways with it. One is to say, well, firstly, from everything we can tell about the environment and evolutionary processes, it wouldn't be that good at a halting detector or verifying the correctness of the halting detection. But even if we, ignored that and ignored the fact that that doesn't seem to be true of evolution, if it were true, that would be really impressive. And, even bigger question of why evolution was so fine-tuned to correctly sort of verify our partial halting detectors during the process of evolution.
Okay. Is there anything like with the pattern detection stuff? Are there any obvious parallels with the intelligent design movement that you want to comment? Like, because I've seen it sort of play out both ways, and maybe this isn't even like the right dimension of the analysis. I'm not even sure what the language is. I've seen people say, like, oh, the fact that we can see all this complexity and everything and it's all reducible to a few simple, rules, doesn't that prove that there must be this incredibly intelligent designer? That, you know what I mean? Like that, like, doesn't it show there's a pattern involved? So clearly there's some intelligence but then I've seen atheists say, no, it's the other way around. That, yeah, we see all this stuff and what looks like it was designed, but no, if we could actually explain all this multiplicity of various, life forms and organisms and body types and all this stuff, quasars and it all just is a result of a few simple laws of physics and matter and energy, then, that's what it would look like to show we don't need to invoke an intelligent creator, is to be able to discover, parsimonious. So it's interesting that they both agree on what's going on, and one says clearly there must be a God, and the other one says clearly there's no need for a God.
Right. So certainly when we think about pattern detection and the short descriptions, it's actually sort of dovetails a little bit into I was recently a co-author on a book with William Dembski, the second edition of the Design Inference, which Bob knows about, but I'll say for the reader's purpose. And here's a copy of the book here. It's just come out. It's the second edition. It's the 25-year edition. So I was not old enough to be involved writing books 25
So was it an improvement over the first iteration?
Yes. I was involved, so it must have been an improvement, right?
I was going to say, did the original authors realize that, yes, this is an improvement?
Yeah, so the original author was still heavily involved, and he invited me to come on and help him there. So one of the things we look at is design detection, inferring when can you infer something is designed and when not. And part of the answer is that it needs to be what we say is specified, which essentially is that it follows a pattern. And we actually evaluate that using the idea is, does there exist a short description for it? And that's very much the same idea that was being invoked in the pattern detection thing is there a short description for it? And so to infer that something is designed, it can't have a very long description because that would be random. You don't infer design for random things. But we have short descriptions. But the other side of the design equation is that it has to be improbable. It has to be unlikely to arise by chance. And so some cases, it has a short description, but it's also likely to arise by chance. So if you look at like a quasar, I don't know the astronomy behind quasars, but my assumption here is there's a relatively simple process by which quasars develop, and thus there's a high probability of quasars forming without some sort of intelligent intervention. So we say that's high probability. So even though there's a simple description for what a quasar is, we wouldn't infer design just based on that because it also is a low probability. But we look for things which have short descriptions, but also very low probability. And we argue that when you look at things like biological life, that they actually have a very low probability of arising. And so course, the sort of mainstream evolutionary viewpoint would say, no, 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 there's a very simple explanation for all the complexity in life, Darwinian evolution. And it's, all we need is random mutations, natural selection, and everything emerges. Now, a large part of what the intelligent design community argues is that's not true. Evolutionary process wouldn't actually produce the kind of things we're seeing here. And of course, that's a whole big argument in and of itself, which probably don't have time to get into here. But the essence of the point is that we argue in those cases that in that case, it's not like, oh, it's simple, and therefore there's no reason to for design. We argue, well, it's simple in the sense of there being a simple description, but it's actually highly complicated in the sense of being very low probability of arising.
Can you give an like a more trivial or humdrum example of that distinction? When you see something that's clearly designed, like in how specified complexity.
Let's take a book.
Mm-hmm.
We got a book. There's a bunch of words. So in some sense, there's a very simple description here. This is English text. Now, if you were to sit a monkey in front of a typewriter and let him bang on the keyboard, assuming you can keep the monkey interested for long enough, you might get a manuscript this long, but it wouldn't be English text. So we would not infer design based on the monkey's manuscript because there's no longer a short description. But we do infer that someone or a bunch of people were involved writing this book because, it actually makes, English text with coherent arguments in the book. And that is something that has a short description, but it's very unlikely that just by chance that would be those words would show up.
Okay. And so what I like about the whole Dembski and, the specific is that you're trying to be rigorous and to say, let's not look at biological phenomena right now. Let's first just deal with everyday stuff and what does it mean? The examples, that I like to use is you're flying in a plane and you look over an island and you see like the rocks have been arranged to say, shipwreck help or something. And whoa, there were humans involved with that. Yeah. That is not just that, well, no, I mean, the rocks could have rolled down and blah, blah, blah. Like, no. And then when you just try to think through, why are we so sure that we see signs of intelligence? You can go through that and then go ahead and just go through and come up with different examples. And what if you saw a bunch of rocks, but they didn't seem to be spelling anything out? Then you'd be willing to say, yeah, I'm open to the idea that there was no intelligence involved with that pattern and it really was random and blah, blah, or mindless, if you want to use that word. Okay. And then the idea is that when you pin that down and rigorously, like come up with, quantitative ways of assessing for a given thing, given the environment, what you're talking about, the nature, the space of all possible things you could be analyzing. If you get rigorous and say, what does it mean to say we see signs or evidence of intelligence or not? Okay. And then once you have that framework up and running and stuff that we can all agree on, like the arrangement of rocks on a hillside, and we see signs of intelligence, you go deploy that to organisms and that, the biosphere, and design's just jumping out all over the place. Is that?
Yeah, that's essentially it. That we basically argue that the design inference, we use it implicitly all the time. And particularly even if you look at fields that are explicitly trying to detect design, such as like investigating whether there's fraud or arson or these things, they are implicitly using the same technique we describe in the design inference. And we think if we just apply those same techniques to fields of biology and physics of the universe and such, we think we come to a conclusion of design.
Well, what I thought was hilarious, it's a somber topic, so maybe hilarious is not the right word. But when, during with COVID and when people were arguing about did SARS-CoV, I forget now what the thing was.
SARS-CoV-2 something?
Yeah, I was going to say SARS-CoV-2, but I forget what the 2. Oh, it's because it was the second version or something. Anyway, they were wanting to know, was this bioengineered in a lab? Did humans make this thing? And I was waiting for all the Darwinians to come forward and say, no. In principle, that question's unscientific. You might as well ask whether, when it's thundering, if the gods are bowling, because that's what we've been telling these idiot intelligent design people for 20 years that they're not just that they're wrong, but that they're not even doing science. To ask whether a biological thing has any evidence of design behind it is stupid, is unscientific, and go back to reading, and yet here we are trying to use scientific measures and microscopes and blah, blah, blah to figure out, is this thing, does this show, could evolution have created this thing, or was it made in a lab? And so anyway, it was just funny to me that
Yes, definitely. It felt like there's a double standard in applying the design inference, depending on how much you don't want that designer to be there.
Yeah. So in any event, again, that just going through that little tirade on my part doesn't prove that there was a guy 2,000 years ago who walked on water and fed 5,000 people with some loaves. Obviously, by itself doesn't prove. But I am saying just the sophomoric dismissal of intelligent design by some leading biologists, that when the thing was first really picking up steam, and I was hip deep in those debates at the time, like the mid 2000s, let's say, and just how, just showing how I was going to say unscientific, but just the poor philosophy of science behind it, just how much they were just trying to throw it out and just as a category error.
Yeah.
And no. Well, and again, a popular thing I use a lot. I'm just saying that I know you've heard this a million times, Winston, but for those that in principle, it's possible that humans were, seeded here, that intelligent aliens, whatever, 500 million years ago, who knows when, came and deliberately engineered, certain cells that had all the precursors necessary for our bodies and planted them somewhere, and they started multiplying and blah, blah. That's possible that that's where we came from. And yet, according to some of the people who try to dismiss intelligent design, just out of court, that we would never be able to discover that, or scientists wouldn't, at least. That's not a question that science could ever answer. And that just seems nutty to me.
Yeah. It's definitely very suspicious when someone's trying to rule your position out of bounds, sort of on principles of sort of the ideas of boundaries of science rather than where the evidence is. And it's also particularly ironic because if you look into the definitions of science and such, it always comes down to, these are the areas where science can't pronounce and can't say yes or no on. And they're like, well, but they very much do want to say yes or no on these questions. But that, I think I lost my articulation somewhere in the middle there. So they often try to rule out my laptop battery signal just came on, so I'm going to go plug in.
Okay.
Before I lose anything here.
Okay.
Is that really bad? Okay.
That program was going to halt. Am I right? Okay. So
yeah,
last big thing I'd just like to ask, and then, we can wrap this up, is besides these more important metaphysical questions, what relevance or what impact does your discussion here have on the possible limits on AI?
Right. So if I'm right, and basically we're only capable of creating artificial intelligence less smart than us, I think that, puts a limit on some of the more fantastic speculations of some people, because I know some people have ideas, well, we're going to create an artificial intelligence smarter than us, and it's going to create artificial intelligence smarter than that. And there's going to be such a rapid explosion of intelligence going to lead to the singularity, and then the whole universe will be changed. No, because an intelligence, and I think it's intuitive, can only create an intelligence less intelligent than itself. And so we're going to be limited. Now, I think it also helps understand in this day of ChatGPT and all that, what kind of limitations we expect here. We expect that, yes, we can get progressively closer to our own intelligence as we sort of continue to work on these things. And we would expect, yes, ChatGPT is going to be followed by progressively better artificial intelligences, which I think are going to approach, but never kind of reach a human level of intelligence. And also, I think if you look into the details of how these systems work, that, ChatGPT is really a couple of good ideas put into the system and a lot of training data. And I think there's going to be some new good idea that people add into ChatGPT to improve it even more, just sort of the same way that you might be able to improve those partial halting detectors, because ultimately all the tasks ChatGPT are doing are equivalent to partial halting detectors. And so I think that gives you a way to think about sort of what AI does and how AI can progress in the future.
What's funny, Winston, is there's you and I know 3 other professional computer programmers, or at least one of the guys, like I think that's a true statement. And all of you are less optimistic about the potential of GPT than I am, which is, one might have thought it'd be the other way around, that the people in the computer science are really excited about this, about their baby. And yet it's like, no. This kid's, he's good for nothing.
Some of it is, we understand how the sausage is made.
Mm-hmm.
And it's invariable that when you understand how the sausage is made, it seems less impressive.
Right. So
sometimes that's not entirely fair. Sometimes the sausage is really good, but because you made it, all the gross stuff in it, you can't stomach it. So likewise, I think we can be a little bit jaded on what the technology can do, because we're like, man, it's just numbers.
Well, real quickly, I don't want to take us on a different tangent here, but my deal with that is, I don't understand it as much as you do. And I also have in mind Gene Callahan. He said it on this, I won't name the other people just because, it was a private discussion. I don't know if they want me talking about it, but I know enough. Here's where I'm coming from, Winston. I know enough about, how they train these LLMs and everything to realize, or to believe the stuff I'm seeing, the conversations, put in quotation marks, I have with GPT-4, there's no way that should be, this thing should be spitting that out, is what I'm saying. Given what I know, how crude and simplistic the training was. And so that's why I think, no, there's something in word itself, and I, ties into the Gospel of John and everything in my framework, that, oh no, there's something special. Like the fact that it trained on language and words is because there was more packed into there than we humans put into it. That's what my deal is. So I fully appreciate how simplistic the training is. And so you could think, well, there's got to be some ceiling on that. And in my view, it's already broken way through where it should have been contained in. Meaning,
So
go ahead.
I remember seeing, I think it was GPT-2. Mm-hmm. And at that point, GPT-2 was like, it was, not nearly as good as GPT-4, but it broke my intuitions at the time for what computer technologies could do. Mm-hmm. Realize, okay, we're coming to a point where they can like generate free-form text and have, somewhat sensible responses to questions. And so, I'm actually, I think, more on the optimistic side in terms of ChatGPT's abilities than many people who are like poo-pooing it. I think it is very sophisticated and very impressive. But it's also clearly not human level intelligence. And I think it fits nicely in line with sort of my framework of thinking about that progressive line of intelligence.
Yeah. So what's interesting, I agree it's not there. And something just happened the other day that I realized illustrated this distinction or the chasm still, that, so for my company Infinio, we have deployed what's called AI Bob, as you can guess what that is. There's a certain Facebook group that we have that pertains to the way you use life insurance for cash management, that we do at Infinio. And so I right now am overseeing AI Bob. And so someone posted like a meme. I can even say what it is. It'll make the story better. Someone posted a thing, like it showed like a billboard, and it said, my boss wanted me, or it was something like, my boss wanted me to get interested in a 401k, but there's no way I'm running that far. Okay. It was something like that because it's a financial deal, right? And so I was curious to see if we just take that exact text and pop it into, because we have our AI engine that is supplemented with like my writings and so, that's why it's AI Bob. It's not just GPT. Right. So I just took that with no external prompting or anything and just plugged that in to see what would it say. And it went, there's been some confusion here with an exclamation point. you're thinking it meant blah, blah, blah. No, actually, what the 401k is in the U, and it correctly explained what a 401k was, and then it ended and said, so you see, your boss wanted you to contribute to your financial future, not work on your running endurance, exclamation point. And I was blown away that it knew to use, normally it doesn't use exclamation points. So it recognized that there was something jocular about this situation. But of course, what it missed was that the person posting that was making a joke. You know what I mean? Like, it thought it was an earnest misunderstanding, not a joke.
It's kind of the uncanny valley a little bit of the.
Yeah. So you're like, it was like 2 levels, but to be human was be 3 levels or something.
Yeah.
And then what's also interesting is, so I, posted the response in the thread, because I was impressed. And so I'm there, like the Facebook account, it looks like AI Bob posted the response, because I was logged in as that. But I wanted to let everyone know what had just happened. And so then I put an open brackets, for the next comment. And I said, hey, everybody, this is the flesh and blood Bob Murphy. I'm too lazy to switch Facebook accounts. I just want to give you the context, and I explain what happened. And then later I was thinking about it and realized, like, that right there, I knew at least at the level of what these LLMs can do right now, I was able to signal to everyone. So they're pretty sure, no, this is the real Bob talking. This isn't AI. You get what I mean? And like, by me saying, I'm too lazy to do this, this is Bob Murphy, not this is Robert Murphy. You know what I mean? Like, so presumably GPT-9 would be able to do that. You know what I mean? Like, and be able to, and so if GPT-9 right now existed and we're going, or this, the CIA's version of it, maybe it is fooling us, and we think we can tell the difference between a bot and a human on Twitter, but maybe not the CIA's LLM or whatever. But I'm just saying, so that kind of showed that, yeah, as cool as and as impressive as I was still very easily able to tell the other humans, this is a human talking right now. Mm-hmm. And in a way that just using, not because I went over to their house and touched them physically, but just using the same, medium that the LLM was using, I could convey the information, like a pretty reliable signal that this is a real human typing this. So, and your point is, you think even though GPT is going to get more and more impressive, you don't see it breaking through and becoming more, because in a sense, how could we create something that was more sophisticated than us?
Yes, that's my point in a nutshell.
Okay. One quick last one on that. Surely I can have a son who grows up to be more intelligent than me.
Yeah,
so
but
how do you
didn't build your son in that sense. Your son, of course.
Let's keep this PG. So, I mean, I'm being a bit tongue in cheek, but I also, that would help to explain. Yeah. So can you just walk through though,
so
again?
Your son, of course, is made of a combination of genes from you and his mother. Mm-hmm. And that essentially contains some sort of program in it, and the details of which we have, we're just starting to understand. And that program develops and produces the mind or the brain that your son will have. And so you didn't have to understand the process of that mental development in order to have a son. And, even, animals and such all manage to do it without any comprehension of sort of the mental development process at all, because it's not really you who's doing that. It's actually the genes that are responsible for that, the development of your son. And if your son got a better combination of genes than you, and, also, various developmental processes that are involved, if your son has better nutrition or, was less traumatized by childhood events, or who knows, all the factors that come into play here, all of those are going to influence how well that program plays out and works. But your intelligence, of course, doesn't really have anything to do with it, because you're not actually one responsible for building that intelligence. It's your genes. And of course, I think those genes ultimately derive from the creator. Okay.
So I get that. Couldn't somebody, this last one, I'll stop. Couldn't someone say though, okay, Winston, you're right. If we were just sitting down and trying to directly using C++ write out GPT-5, we agree, like in principle, But that's not what's going on with these things. In fact, a lot of the researchers involved with GPT are saying it's a black box. They set up the training and it goes and does its thing. And when you say what's actually going on inside when it answers this prompt, and at some point they're like, we don't know. We just tweak the thing and we can evaluate the outputs and say whether they're better or worse. But at some level with this thing, this is more of a black box than, computer programs 20 years ago were. So how do you feel about, and so if that, in that sense, then why couldn't it eventually be more intelligent than us? Because it's not that we sat down and thought, let's go ahead and build a system smarter than us. That no, we kind of just let the thing run and it stumbled around and discovered this, better setting for its knobs on the, different parameters such that predicting the next token is even more accurate than what we could do.
Right. So, so it's built on these ideas of these neural networks and these training things and particular ways to structural neural networks and how to parallelize them on GPUs. And those are all various very clever ideas that people have had that were put together. And that's what makes ChatGPT work. And it's all directed towards the goal of trying to help build a smarter algorithm that is able to take the training data and figure out how to sort of predict the next token. That's still limited ultimately by the sophistication of that training algorithm. And once you've put all that training in, how the internals of those neural network works, that's a very complicated black box. But I think what it comes down to is it's all back to the sophistication of that training algorithm. And the sort of big moves, the big shift with ChatGPT partially is that we've just developed more sophisticated training algorithm. And so it's actually that training algorithm that's the key contribution of the humans there. And then they've also put a huge amount of effort in collecting the data to train it on. And that's all produced by humans, and they've put that all in there. So it's still, in my mind, yes, it's humans with their sophisticated training algorithms they've come up with, plus their human data. And it's still all sort of deriving from humans in that way, even though they're not consciously understanding all of the details of the internal neural networks. But we've just figured out how to build systems that can figure out neural networks. And we're still limited by sort of the sophistication of those training algorithms.
I promise this is the last thing I'll say. It does seem like there's some weird flipping back and forth that I can't quite put my finger on where, because even as I was like trying to give that objection to you just to hear what you had to say, at the very end of the argument, I realized there was a little bit of something going on there where maybe loading the deck where I said, and then we don't know what's going on. And then it just keeps checking. Maybe it discovers a particular combination of those dials such that it's better. But even there, I realized, and I said, predicting the next token, but that right there, what does it mean to say success? Like the humans are the ones who are saying, whether this system does better at predicting the next token. And so, because what we mean is, does that look like something a human would have written? And that's what it means to say it did a good job of predicting what the next token would be in this sequence of words. And so it is a kind of an odd thing. But yet on the other hand, and I even thought too with like AI bot, like partly what we're doing internally at Infinio is I'm writing up exams so that when we tweak AI Bob and we'll just let him take the exam and get to see, like, does he understand life insurance and economics better now or worse? And we can kind of evaluate the various tweaks we make in the training data and blah, blah, blah. But then I was realizing as I'm talking to you and listening, would it make sense that I would ever go back to report to the other team members, yeah, guys, at this point, AI Bob's smarter than I am? You know what I mean? Because wouldn't I need to run a test that I know the answers to evaluate him? You know what I mean? So there's that current, but then, and this is the last thing I'll say, and I'll let you have the last word and I'll close the episode. Surely I can meet someone and say, I can appreciate that guy is more intelligent than I am. Like that's you know what I mean? So there's a weird thing like, well, how could you know he's more intelligent than you are? Because then you would have to be, and so anyway, you get the tension.
So you can tell a person is smarter than you when they can actually bring you along and show you the argument of how to get there. If they just start making claims, you have no idea whether they're smarter than you or they're an absolute idiot. But when they can show you, oh, I think this is true. Here's the steps to go you there. You're like, oh, I never would have thought of that. But now you've shown me the steps, I can see there, and oh, I can tell you're really smart. Or, someone could also be smart, just, okay, they can tell you all about these, they remember all the details of all these historical events. That's kind of a slightly different kind of intelligence. And so in principle, right, you could imagine a Bob GPT starting to do there, and you're like, it says something, you think, oh, that's not used to tell, oh, that's not right. And then it comes back and says, no, this is true because X, Y, and Z. And you're like, oh, I have to agree with AI Bob now. He is smarter than me. So that could, at least you can imagine that happening. But I think, given that ChatGPT, that AI Bob has been fed a lot of information, it could actually, that's perhaps not that implausible, that it could start, saying things that you didn't know. And in that sense, you could say, oh, it's smarter than me in certain ways. But I think ultimately, it's still limited by those training algorithms. And I think that we're not going to get to a point where it actually reaches that level of intelligence where you would feel like, oh, in terms of reasoning ability and these sorts of things, it has actually surpassed.
Mm-hmm. Okay, fair enough. That's a fascinating discussion. My guest this week, folks, has been Winston. Is it Ewert?
Ewert. You as in like a baby sheep. Ewert.
Yep. Okay. Winston Ewert. Okay. And with his book, do you have the book handy again?
Yeah, I dropped it here, but I can pick it up.
Yeah, I remember it fell.
Yeah, here is.
When you were trying to prove to us that it wasn't composed of random digits.
Yes. And unfortunately, my movements apparently were composed of random.
Yeah. Minding the
brain. It's models of the mind, information, and empirical science. So there's a variety of perspectives in here on different sort of relationships between the mind and the brain. So there's, lots of mind-bending stuff in there if you want to try and understand all these different points of view people have. They're not all going to be like high computer science stuff. There's like stuff in there about near-death experiences and some philosophical arguments and other scientific arguments. So if you're interested in the relationship of the mind and the brain, I think it's a good resource. Okay, well, great. And do you write, if people who like this conversation, is there stuff they can go to online to see more of your stuff, or? I have a website, WinstonEwert.com, but it's basically just links to my papers and books that I've been in. I don't have like a blog or something I can point people to. Okay. All right. Well, fair enough. If they want to see more of this, then they can go there. If you want to see more, that's the place to go, WinstonEwert.com. Okay, great. So thank you, Winston, for your time. Yeah, thanks for having me on. Thank you, everyone, for tuning in. We'll see you next time.
You've just experienced another episode of The Bob Murphy Show, the podcast promoting free markets, free minds, and grateful souls. For more information and to subscribe to this podcast, visit bobmurphyshow.com.